Hello, how are you? Great that you're here today. I wanted to continue. This is going to be assignment 72, and we're dealing with exponential word problems, number 2. All right. Let's actually start off with some bell work, some local bell work. Tucson in 1950 had 45,454 people, according to the 1950 census. And if we check again a little later, we're up to 521,109 people. So we've had a little growth here, more than 10 times the number of people in the last 61 years. I think it's kind of nice. And so what I would like to do is ask, when will we have 1,000,000 people? And I would also like to know how many people are in Tucson today. Okay, but before we can answer either of these questions, we're going to have to build the model for this. So, can you go build the model for this? I recommend because population grows continuously. Okay, give the video a pause and come back. Hey, welcome back. So my question is, did you leave this as 1950 and this is 2011? Because if you did, this is going to be a much harder problem. I'm happy to do it with you. But for me, I would say 1950 is t equals 0. And so this one is going to be t equals 61 for the purpose of having ordered pairs. Now, why might I want to do that? Well, I've got to find this original amount. And the easiest way to find this original amount is to define 1950 as the original time. If we say 1950, we had this many and not 0 this many, we're saying that this model is accurate all the way back to the birth of the Christ. And no, this model will not be accurate back to year 0. And so I just say, why don't we start with this being time equal to 0? And this is 61 years later. If I take 2011 and subtract 1950 from it, I'm going to get 61. Now, with that in mind, can you finish the problem? If so, go back and try again. Come back when you're done. Welcome back. So if I plug in a 0 here, 0 times r is 0, e to the 0 is 1, 1 times p is 45454. So I know that the initial population is 45,454 e to the rt. But I still need to find that rate, and that's why I need the second ordered pair. This is my time. This is how many people live in Tucson. So 521,109 equals 45454 e to the, we're plugging this in for t, 61r. Well, I'll start by dividing both sides by 45454. And then here, I want this exponent to come down. So I'm going to have to take the ln of both sides. So I want the ln of this stuff, and I want the ln over here, so I can bring that 61r down. So 61r is the ln 521,109 over 45454. And so I don't want to know what 61 times r is. I want to know what r is, so I'm going to divide both sides by 61. Okay, remember, don't round this rate. When you do this on your calculator, the ln of 521,109 divided by 45454, and then we divide that answer by 61, I get a rate of 0.03998 8.78427. There's my rate. So I'm going to take this unrounded rate, and I'm going to take this initial amount, and I'm going to plug them in together. So I'm going to have A equals 45454 e to the 0.0399878427t. I can see that my population is growing about 4% per year across those 61 years. And that's pretty good. It's a robust growth rate. Okay, so now can we answer the questions? Remember, the first question is, when do we get to 1 million people? When? So, what's that? Is that this? Or is that this? Is this a when? Or is this a when? Well, time is a when. And 1 million people, do I plug a 1 million in here? No, this is 1 million people. It doesn't go in for time. 1 million people goes over here for the amount of people that we have. And we're looking for time. When tells us we need to solve for t. So 1 million, 4 e to the 0.03998788427t. So first, let's divide by. And then, how am I going to get this down? That's right, I'm going to take the ln of both sides. I take the ln over here, and the ln over here. I can bring down this exponent. So I'm going to have the ln of 1 million over 45454 equals 0.03998788427t. Fabulous, but I'm looking for t. So I'm going to have to divide both sides by this rate. Well, let's see what we get on our calculator. On my calculator, I get ln of 1 million divided by 45454. And then I want to divide that number by our rate. And our rate was 0.03998788427. And I get t equals 77.3 years. So 77.3 years from 2050. Well, if I add 77 to 1950, I'm going to get 2027 and a little bit more. If I do 0.3 times 12, that'll be halfway through March. Halfway through March in 2027, we should be celebrating 1 million folks live in Tucson. Okay. And the other question I asked, oh, I can't believe I just erased that. The other question I had asked was, what's the population today, i.e. in 2020? Okay, so use your model and see if you can figure that out. I'm going to try and reconstruct it with what's on my calculator. Times, and I want e raised to that number. 4. Okay, well, when I plug in not 2020, but for 2020, that would be t equals 70. When I plug 70 into our model, and remember our model was 45454 e to the 0.03998788427t. But I'm going to plug in a 70 for time. When I do this, I find out that the amount is 746,839.136. Please always round to 3 places. I know you're saying, but how can we have 0.136 of a person, Mr. Kukla? Well, their life is a little more challenging than ours, but we love them all the same, and don't not count them. That's bad. Okay, we're already worried about undercounts with the census, and we only do that every 10 years. Don't discriminate against 0.136 of a person, though I am kind of interested to go and Google what the population of Tucson is today. Ooh, whoa, 971,000 is where we are today. So I guess our growth rate must have actually increased from where we were because we're much further along. We're much closer to 1 million than we were in 2011. Okay, so there's our little review of building models, exponential models, and then using them to either predict when a future event will occur, or given some time in the future, or given that future event, what time will that take place? All right. So today I'd like to look at 4 problems with you. I think it's 4. The first one is actually, I want to talk about these problems where I'm given a graph. And I'm given some ordered pairs like 0, 3, and 2, 300. Okay? I'm asked to write the equation of this. You know, I could certainly go through the process of using PERT here. A equals P e to the RT. Ooh, look, I have the initial amount. In case I don't see it, if I plug a 0 in here and a 3 in here. 0 times R, 0. E to the 0, 1. 1 times P, well, it's just going to be P. And so P equals 3. So even if I don't recognize this on the graph as the initial amount, I can certainly plug that ordered pair into PERT to find out that, yes, P, the starting amount, is 3. So A equals 3 e to the RT. Next, I'm going to plug in this ordered pair for T and A to solve for R. And so I'll have 300 equals 3 e to the RT. Oops. 2R. If I divide both sides by 3, I have 100 equals e to the 2r. If I then take the ln of both sides, I can bring that down. So ln of 100 is 2r, where r is ln of 100 divided by 2. Okay, it's not ln of 50, it's ln of 100 divided by 2. So on my calculator, I come up with ln 100 divided by 2. Don't forget to close this parenthesis on the ln, right? If you just type ln, it opens the parenthesis, you do 100 over 2, yeah, that's not going to work. You have to close the ln parenthesis before you divide. And so I end up with 2.302585095 as our r value. So what's this model going to be? Well, it's going to be y equals 3 e to the 2.302585095t. There's our model. I think this is a bunch of work. So let's try this other way. I mean, I really like that I can use just that PERT model for so many different things, and I can get this. But generally, when I have points on a graph, I'm thinking about y equals a times b to the x as the method for generating this equation. So if I plug in a 0 for x and a 3 for y, what's b to the 0 going to be? B to the 0 is 1. 1 times a is a. And so just like in the PERT model, it was pretty easy to find out one of those constants. Now, what about finding the b value? Well, I'm going to plug in this for x, and this for y, and this for a. and then I should be able to solve for b. So let's see what happens. 300 equals 3 times b to the second. Okay, if I divide both sides by 3, I get 100 equals b squared. And if I take the square root, b equals 10. Now, I know I've been saying all year when you take the square root of both sides, you need that plus and minus. However, in this model, we're never going to have a b that's less than 0. B is always going to be greater than 0, and b will never be 1. Okay? So I'm not going to use the negative 10. I'm just going to use the positive 10. So what's my equation? Well, the a value is 3. The b value is 10. So my equation is going to be 3 times 10 to the x. And that's a whole lot tidier than that. I think it's a whole lot less work than that. So I'm going to use this method whenever I'm given a graph. At least that's generally what I do. Okay? So how is this going to be different if I have instead 1, 6, 3, 24? Again, yes, I can use PERT on this. But again, I'm going to use y equals a times b to the x. Sadly, though, I don't know my a value because this is 1, not 0. If I plug in these ordered pairs here, I'm going to have 24 equals a times b to the third, and I'm going to have 6 equals a times b to the first. Right? I plugged in the 6, I plugged in the 1, I plugged in the 3, I plugged in the 24. Now I've got these two equations with two unknowns, and I need to solve that system. You could certainly do substitution, like solve this second equation for a equals, and then replace this a with what a equals. And maybe we should look at that, but I actually think I want to do this other approach called elimination. Instead of adding one equation to the other, like I do with linear systems, here, because I have exponential system, dividing both sides, one equation by the other, is actually what eliminates a variable. Because look, a divided by a, they cancel. Here, 24 divided by 6 is 4, and here, this b knocks out one of those. And so I get b squared equals 4. Again, b has to be bigger than 0, so b is just going to be 2. Okay, y equals a times 2 to the x. With that in mind, let's plug in one of these ordered pairs to help us figure out what our a value is. I plug this in for x and this in for y. 6 equals a times 2 to the 1. That's 6 equals 2a, or a equals 3. So y equals 3 times 2 to the x is my equation. Okay? Yes, I do expect you to know how to do this. Please practice. Okay. Next, I want to talk about bikini, and not the garment, though the garment was named for this event. Bikini Atoll is a small place in the Pacific Ocean where the United States was interested in carrying out nuclear weapons testing. It turns out that before we dropped the first one in New Mexico as a test to see what would happen if we dropped it, say, Japan, of what would happen, the scientist in charge of the program actually went to the president at that time, President Truman, and said, you know, we don't actually know what's going to happen here because we've never done this before. And we want to bring up something. There's a very small chance that, in fact, when we set this bomb off, it will burn off all the atmosphere on the entire planet. And, the scientists thought that maybe that going and talking to the president about, is this a risk you're willing to undertake? Um, you know, all of us dying instantly. So they did, in fact, go to Truman, and Truman said, no, since you think it's a very small chance, let's just go ahead with this. And they tested it. But really, there were only a couple of tests before the bombs were dropped on Hiroshima and Nagasaki. And so after the war, the United States military thought it might be better if we, did some more of this testing. But we'd really like it not to be on the United States soil anymore. So they found this place way out in the Pacific Ocean. There were some people living there. And in 1946, a representative of the United States Navy went to the chief of the Bikini Heights and said, hey, would you mind if we borrowed your atoll for a little while? We'd like to conduct some tests. And the Bikiniites didn't actually fully understand what was going on. I mean, it was very hard for anyone to really know what was going on about this, not just because it was a top secret project, but because we didn't have an understanding and experience in the way we necessarily do now about the effects of nuclear weapon testing in our backyard. So the chief said, you know what, we like your spam. It's only for a little while. We'll happily move. And so they agreed, and they were moved to a place called Rongerik Island. And the problem with Rongerik Island was that there was no fresh water. So in in 1947, these people were moved again to Kwajalein. It's another tiny island. But what happened there was also not enough fresh water, and they didn't have the ability to get as much fresh food as they needed. And they seemed to be contracting all manner of horrible diseases from the local rat population. So in 1948, the Bikiniites were moved yet another time to a place called Keeley Island. And Keeley Island, wow, that was a pretty place, except that it was only 1/6 as big as Bikini Atoll, and so a lot of people were crowded together in a way that they weren't accustomed. And because of that, someone got careless with the fire, and then suddenly the coconut trees were all burned down. And, you know, things were kind of rough then and there because they now couldn't gather enough of their own food. So the Bikiniites have been rather keen to get back home. Their home was perfectly fine. They quite liked it. In the meantime, the United States, there are really some quite interesting pictures here online, and you might want to Google them. The United States government started dropping nuclear weapons primarily on warships. There were an awful lot of warships after World War II, and so some of the ones that they were thinking about turning into junk, they brought over to Bikini, and they dropped nuclear weapon on them and see what would happen. In fact, there's a ship, I think it's a German battleship, maybe it's just a heavy cruiser, that was brought over actually from was it Europe or South America? Don't recall. But you can actually go diving there now. I will say, though, that in 1947, and we're going to call that T = 0 because it's the first test that we have. In 1947, there were registered to be 72 millisieverts of, I think this is cesium. Yeah, cesium-137. Um, cesium-137. Okay, 72 millisieverts present. Now, what does that mean? Well, it was determined that 4.2 millisieverts was too hot to eat the local food. And that really you wanted to get down to at least 2.4 millisieverts in order to feel comfortable and safe about living in that place. And what was it in 1947? Yeah, so it's pretty hot there right now. And so the Bikinites didn't get to go home then. Instead, they stayed away, and the U.S. government, because Keeley Island couldn't provide enough food, the U.S. government actually brought food and fresh water decade after decade. Yeah, kind of expensive, but a thing to do. So, in the meantime, the natives there were starting to say, hey, wait, our ancestors, our older generation is dying off now. We really need to, get back home. So they lobbied, and in 1967, 20 years later, uh, they said, okay, and the they in that sense was the United States government, a plan to return the islanders. The Atomic Energy Commission said that the soil and water tested clean. And as a result, a plan was drafted to move these people back home. That plan took in effect in 1972. In 1972, the people were returned to Bikini. And then, a funny thing happened. By 1975, it turns out that there were an awful lot of people who were getting cancer on Bikini Atoll. And when this was investigated, it was determined, in fact, that both the fresh water that they tested and the coconuts that they tested were well over the safe limit. And isn't that really awkward? So they were moved again. But this time, they got themselves a lawyer. And that lawyer started fighting the U.S. government in 1978. And the result of this legal intervention was to get a court decree to make the place safe to live in. So then, no, it's a very interesting story. So then, from 1978 to 1997, the United States went there and stripped off the top 15 inches of soil. And what did they do with all this soil? Well, they put it on barges. They took those barges out into the ocean, and they dumped all that soil. Because it was thought that if we removed the top, foot and a quarter from the whole island, that we could now be safe there. So the lawyer they're still working on this case. So here's what we want to know. Okay, ready? There were 72 millisieverts in 1947. The half-life of cesium-137, that's what we were testing here, is 30 years. Now, can I just say, that means in order for us to have half the original amount, we got to wait around at least 30 years. This was the original amount. This is the safe amount. We know that if this is the half-life, there's no way for this to become this in anything less than 30 years, but in fact a lot more than 30 years. So I get the feeling that someone was a little disingenuous when they said to the chief, yeah, you'll be home in no time. So what I'd like you to do is use this half-life information, use this original amount to figure out when it will be safe for the Bikiniites to go back home. Okay? All right. You're using this to build a model to help you find when we get to 2.4 millisieverts. Okay. Did you have luck building that model? I used Q equals Q sub O e to the KT because I was talking about quantities. You could use PERT. So 72 is the starting amount. Do you remember our shortcut for finding K in half-life problems? It was the ln of a half over the time for half-life. So I'm going to plug that in here, e to the ln of a half over 30 t. Now, does this number go in here, or does this number go over here? This is not a time. We're trying to figure out when the time is, so I have to put my 2.4 over here. So if you didn't get this far before, will you please finish solving this? Pause the video, finish solving, see what you get, and then we can compare answers. Hey, welcome back. So I'm going to divide both sides by 72. And that's going to be 0.033333333 equals e to the ln of a half over 30 t. I want to bring this down so that I can get access to that t, which means I'm going to take the ln of both sides. Okay. Once I've taken the ln of both sides, I'm going to see the ln of 0.033333333 equals 1/2. Ooh, it's the ln of 1/2 over 30 t. So if I'm trying to solve for t, I'm going to multiply both sides by 30 and divide both sides by ln of a half. So let's see what happens. I'm taking the ln of this number, and then second answer. Okay, and I'm multiplying that number by 30, and then I'm dividing that by ln of a half. And I end up with 147.207 years. Now remember, our initial amount, that initial amount that we had of 72 millisieverts, that came from 1947. So what happens if I take time equal to 0 and add this 147 years to it? 1947 plus that answer, and we're looking at 2094. It will not be safe until 2094. Why? Why did the U.S. government tell these people in 1946 that they would be home soon if the math that was known at the time, this isn't new math, if the math tells us very, very easily, yeah, it's gonna be a while. Sadly, though, the Bikiniites' problems have increased with climate change and waters rising. They're now suffering from nearly constant flooding on their atoll, and some of the pictures I saw of the nice people living on Healy are actually walking ankle deep in water all the time. So, yeah, cautionary tale. Okay, the last thing I want to talk to you about today deals with a young man walking home from school one day, and and he actually, his path home wasn't always on streets. Think of him as here walking through the desert to get home. And he, by the way, this is 1957, and his name is Arthur Andrew. And he lived in Illinois. He was walking home one day in high school, and he walked through this wash, this dry riverbed, and he saw, as he was walking across it, he saw this really interesting rock. So he went over to this rock and looked at it, and you might want to Google this guy from Illinois, and I think actually you want to Google this guy and museum in Illinois. He dusted this rock off and realized that what he was looking at looked like a giant molar, like one of your big back teeth, but huge, like head-sized. So he just thinks it's nifty, and he actually believes that what he's found is an elephant tooth. Now, elephants aren't normally thought to be native to Illinois, and so he put it together with the idea that when he was younger, the circus had come to town, and there must have been something that happened so that this elephant tooth, got stuck here in this wash. Okay, so he's got this elephant tooth, and he graduates from high school, he goes off to college, he actually becomes a lawyer, and then when he retires, he finds this elephant's tooth sitting in his stuff. He's packing up to retire, and he looks at it and he says, well, what is this really? And so he goes over to the university and says, hey, can you tell me about this? And so they ran a test on it. They carbon dated it. And carbon-14 has a half-life of 5730 years. Actually, the number goes between 5700 and 5730. I believe our textbook is fond of 5715. Most sources I find use 5730, and so I'm going to go with 5730. Okay, so 5730 is the half-life for carbon-14, and what they noticed was that only 27% of the carbon remained. And that was a very interesting number. If this were an elephant tooth from the last circus, this should have been something like 99% of the carbon remained. There's a lot less of the carbon. So, can we figure out how old that tooth is? Because if we could figure out how old the tooth is, we might be able to figure out whose tooth it was. Okay? So, first, a conversation about percent. Percent is what you have over what there was originally. What do I mean? Well, if you take a 100-point test, originally there were 100 points, and you got 87 of those points, you have 87 out of 100, we know that to be 87%. But if originally there were 90 points on your test, then again, the percent is going to be 87 divided by 90. We can certainly check that on my calculator. 87 divided by 90, and I get 96.667%. Okay? So really, percent is just what you have over how much there was originally. Or we could say what you have is Q, and what you have originally is Q sub O. So in a problem like this, where we're told 27% of the carbon remains, well, we can think of that word percent as being Q over Q sub O. So I know that Q over Q sub O means percent. So let's go back to our equation. Remember this equation. Q equals Q sub O e to the kt. Okay? If I can make this have a Q divided by Q sub O, then that's going to be percent. And I can plug this number into that place. Okay? So to do that, divide both sides by Q sub O. Look, Q divided by Q sub O. Why, that's our definition of percent. I don't need to know what the original amount is. I don't need to know how much there is now. But when I divide how much there is now divided by what there was originally, that gets me percent remaining. I know that there's 27% remaining. So I can say 0.27 equals e to the kt. Why? Because this is percent. And in our problem, they did that carbon-14 testing and determined that 27% remains. So where do we go from here? Well, let's talk about half-life of carbon-14. Remember what I said about it? Half-life of carbon-14. So the half-life of carbon-14, our book is using 5715, I think. I generally use 5730. The range is actually 5700 to 5730, and so, yeah, I can see why 5715 is kind of smack in the middle. So let's use 5715. I'm not going to use 5730, but yeah, after this problem, I'm going to use 5730. So this is my half-life time. Do you remember our shortcut for finding K in half-life problems? That's right, ln of a half over time to half-life. So I'm going to put this in here. And so now I've got 0.27 equals e to the ln of a half over 5715. No, 5715 t. I'd like to solve this equation for t, which means I'm going to have to take the ln of both sides. This can then come down. ln of 0.27 equals ln of a half over 5715 t. And so if I want to get t by itself, I'm going to multiply both sides by 5715 and then divide both sides by ln of 1/2. Why don't you pause the video and give this a try. See what you can get. Okay, so I got 10,795.456 years old. If only 27% of the carbon remained, then this tooth must be almost 11,000 years old. And that's why we know that the youngest mastodon ever found evidence of in the United States was this one. This is the tooth from the mastodon, the youngest one we've got. 10,000 years ago, yeah, we got humans. And we also have a little mastodon. Hi, mastodon. By the way, when the university tested, they came up with 10,775 plus or minus 35 years old. Look at our calculation. You know a lot of powerful math. It's true. You can do all kinds of things with this math, including figuring out how old that bone was. Yeah, remember, when you see percent, it's Q over Q sub O. Divide both sides by Q sub O, take Q over Q sub O out, and put in that percent number as a decimal. Please don't forget our half-life shortcut. That will be useful. Okay, so I encourage you to practice more of these problems. through the homeworks or synchronous Zoom problems. And in the next video, we'll do one more day with exponential word problems before we move on. All right, have a wonderful day, everyone. Take care. Let me know if there's anything I can do to help.